Well, our last section with composite functions will play into one-to-one functions and inverse functions, and specifically inverse functions. If f is an inverse, then f of its inverse will spit out x, and vice versa. G of its inverse will spit out x as well. We'll get to that. But let's talk about one-to-one functions here initially. First of all, to be a function, for f to be a function, if you remember, to be a function for every x, there is one y. Do you remember that? In other words, it had to pass the vertical line test just to be a function, right? So for example, x squared, does it pass the vertical line test? Yeah, it only hits once, right? So to be a function, it's got to pass the vertical line test first of all. And then after passing the vertical line test, it'll have an inverse only if it's one-to-one. Only if it's one-to-one. So that means if f of a is not equal to if a is not equal to b, then f of a is not equal to f of b. In other words, for every y, there's a unique x value. For every y, there's a unique x value. All right, so for example, look at x squared for a minute. For this a and this b, see how they have the same y value? It fails, it's not one-to-one. It's saying if f of a cannot be equal to f of b for different a's and b's. Okay, so that's called the horizontal line test. Test that. If I run the horizontal line test through, if it hits more than once, it fails. So this is not one-to-one. So y equals x squared is not a one-to-one function. It does not have an inverse, is what it's saying. It does not have an inverse. It fails the horizontal line test. So this first one I say, well, is it pass the vertical line test? Yes. So it is a function, letter A. Does it pass the horizontal line test? Yeah. Good, he's right. So fails miserably, right? It hits 3 times. Again, it can only hit once. So fails the horizontal line test. So this is not one-to-one. In other words, it does not have an inverse. B is a function, passes the vertical line test. Does it pass the horizontal line test? Does it only hit once every time I test it horizontally? Yeah. Passes the horizontal line test. So this, yes, is one-to-one. This is a one-to-one function. In other words, it has an inverse. The third one, is it a function? Not a function. So it can't have an inverse anyways. I know it passes the horizontal line test, but I don't care because it's not even a function. So since it's not a function, there's no way I can have an inverse. Now, so inverse functions. So if f and g are inverses, so if f is a function, and f is one-to-one, then it has an inverse, and we'll call g. G is the inverse of f. G is the inverse. Well, if it's an inverse, then this will be true. It'll satisfy both of those conditions. Their composite, f of g of x, will be equal to x, and g of f of x will also be equal to x. Okay? So let me give you a little bit more on that. So like for example, let's say I had the function, here's f of x being squared x minus 2. And notice I have like the point 2, 0. I could plug in like 6, square root of 6 minus 2 is square root of 4 is 2. So I have 6, 2, and so on, right? Its inverse, so I'm going to call g. Instead of having 2, 0, would flip that around. So instead of 2, 0, it would have 0, 2. Instead of 6, 2, it would have 2, 6. Because it's an inverse, right? And everything else, anyways, you flip all those points and it kind of looks like that. And if you notice, these are a reflection about the line y equals x. In other words, when I run their composite, f of g of x, they undo each other and just leave you with x. Same thing when I do the other way around. If I go g of f of x, they'll undo each other and just leave you with x. Because they're mirror images about that line, the identity function of y equals x. You see how they're reflective about that diagonal there? So the points flip-flop, right? So let's look at this one. If f of 10 is 14, and I should say, what's this notation right here? You know, we call g as the inverse. That's f inverse. F inverse, right? It doesn't have to be g. We're going to call it f inverse or f inverse of x. F inverse of x. We've been using g up to this point, right? So that's f inverse. Well, if f of 10 equals 14, in other words, you have the point 10. Oops, that's not very good. You have the point 10, 14 right here. If that's on f, what would the point be on the inverse? 14, 10, exactly. So in other words, f inverse of 14 should spit out 10 because it has the point 14, 10. This one had the point 10, 14, right? Remember, they're reflective about the line y equals x, right? Again, I don't know much about anything else on this, but I do know they flip-flop, right? So let's go ahead and verify. These two are inverses. F and g are inverses. In other words, g of x is the inverse of x. You could call it f inverse if you wanted to, right? Let's go ahead and verify that they're inverses. Well, if f and g are inverses, then f of g of x would be x. And, number one, I'm going to check that. Number two, I also have to verify that g of f of x equals x. So we're going to go ahead and verify that algebraically, and that'll prove it. That'll prove it. And we'll actually do the visual first on this. Let's do f of x equals 2x minus 1. Well, that's a linear equation with a y-intercept of negative 1, and it goes up to right 1, up to right 1, because the slope is 2, right? Slope is 2. So you could graph, here's our f function. Here's f. And g, which we're calling the inverse, is 1/2 x plus 1/2. So it has a y-intercept of a half. And it goes up 1, right 2, up 1, right 2, up 1, right 2, and so on. You could check a couple points, like f has 2, 3. So if they're truly inverses, then the inverse should have 3, 2, right? And so on. So they flip-flop. All those points flip-flop because these are reflective about that line y equals x. There's y equals x, right? They're reflective about that line. Well, visually we can see it, but let's go ahead and prove it algebraically. So I'm going to go f of g of x. Well, g of x is 1/2 x plus a half. And I'm only working with the left-hand side. I got to make sure that it's equal to x at the end. So f is 2x minus 1. Well, g goes in. 1/2 x plus a half. Distribute that through. That's x. Sure enough. Did it equal x? Yes, it did. So condition 1 is met. Now I'm going to go g of f of x. G of, who's f of x? F of x is 2x minus 1. G is 1/2 x plus a half. Again, I'm just working with this left-hand side to make sure the left-hand side simplifies down to be x. That's what I'm wanting. Distribute that through. We got x minus a half. I still have that plus a half. Well, those are gone. Sure enough, x equals x. Satisfied 1 and 2. We just proved that they are inverses algebraically. That's how you verify that they are inverses. No. Ah, there we go. All right, let's keep going here. I've got, make a little note, right? This F inverse, as we've mentioned, that's F inverse. That's the inverse of F. That is not to a -1 power. That's F inverse. All right. Notation. All right, let's go ahead and verify these ones. Well, if F and F inverse are inverses, then number one, their composition, F inverse, must equal x. And number two, F inverse of f of x must also equal x. Let's go ahead and prove that. So F of, who's our inverse? Well, the inverse is x squared plus 3. F is square root of x minus 3. And F inverse goes in. X squared plus 3 goes in. Let's see if this works. Oops. All right. So we got x squared plus 3 minus 3. You notice those 3's cancel. So you're just left with squared x squared over x. Does that equal x? Yes, we were trying to see that it equaled the right-hand side. So condition number one, we're okay. Condition number two, F inverse of f of x, which is squared x minus 3. Does that equal x? Okay, now I'm working with F inverse. Well, F inverse is x squared plus 3. What goes in? Squared x minus 3. Well, the square will undo the radical. So we get x minus 3 plus 3. Sure enough, we got x. Yes, it does. It does work, right? And by the way, if it didn't, like I'd get to the end and I'd have like, does 3x equal x? I'd say, no, it doesn't, right? And I'd say, nope, they're not inverses, right? So that's how you want to verify if you are inverses. Well, let's go ahead and find some algebraically. So here's the steps that we're going to go to. Number one, we're going to replace f of x with y. Number two, we're going to switch the x's and y's, because if they're inverses, the x's and y's will flip-flop those points. We're going to solve for the new y. And number four, we're going to replace that new y with the inverse. That's our inverse. So let's go through it on this one. So here's f of x, 2x minus 5, right? F of x is a nickname for y. So number one, replace f of x with y. Now number two, switch x and y. So this becomes x, that becomes y. Number three, solve for the new y. So I'm going to solve for the new y. X plus 5 equals 2y. In other words, 2y equals x plus 5. Divide everybody by 2. Y equals x plus 5 all over 2. Number 4, that new y is f inverse. So replace it with f inverse. This is the inverse function. X plus 5 all over 2. In other words, if you were to graph 2x minus 5, and then you were to graph 1/2 x plus 5 halves, you'd see that they're reflective about this line y equals x. I didn't draw that very well, I know, but they're reflective about that line y equals x. Right, and you could also verify that very quickly if you wanted as well, right? You'd say, well, if they're inverses, f inverse must equal x, and f inverse of f must also equal x. So let's do the first one. F of f inverse is x plus 5 over 2, and f is 2x minus 5. So I have 2x minus 5. Notice the 2's cancel, so I get x plus 5 minus 5. Sure enough, that one worked. Now let's do f inverse. I'm sorry, f inverse of f, and f is 2x minus 5. f inverse is x plus 5 all divided by 2. Well, 2x minus 5 plus 5, minus 5 plus 5 is gone, so I got 2x over 2, which is just x. Does that equal x? Sure enough, it does. So we just verified that we did that correctly when we found the inverse. Let's do some more here. So this one we got f of x is squared at x plus 7. So that's our y. So step number 1, replace f of x with y. Step number 2, switch x and y. Right, number 1, f of x with y. Number 2, switch x and y. Number 3, solve for the new y. Well, in order to solve for the new y, I got to get it out of the radical. So I got to square both sides here. So I got x squared equals y plus 7. Now y plus 7 is free of that radical. I subtract 7 from both sides. So I have y equals x squared minus 7. Now I name it the inverse. In this case, it was f was the original function. So f inverse is x squared minus 7. Right, and then we can go ahead and verify that, right? So we have f of x is supposed to give you x. So f of x is squared x plus 7. Oh, I'm sorry, f inverse. I did that wrong. Sorry. F inverse. Our inverse is x squared minus 7. F is square root of x plus 7. So x squared minus 7 goes in. Minus 7 plus 7, gone. Sure enough, x equals x. Let's do it the other way. Does f inverse equal x? Well, f of x is squared x plus 7. And f inverse is x squared minus 7. Well, that'll undo the radical. So we're left with x plus 7 minus 7. So sure enough, x equals x. And we again verified our work that truly is the inverse there. This next one, there's some pictures of it, by the way. So, and I should talk about this as far as the picture is concerned. Originally, we have x plus 7. So it's the square root function, but it's moved left 7. There's our f function. Now, if you think about our inverse, we said this inverse is x squared minus 7. But if you graph x squared minus 7, doesn't it look like this? Well, it can't be both, right? I got to have all these points from square root of x plus 7, such as negative 7, 0. That's got to flip-flop. Another one would be like negative 3, right? Negative 3 plus 7 is 4. Square root of 4 is 2. So negative 3, 2 would have to flip-flop. Another nice one would be like 2. 2 plus 7 is 9. Square root of 9 is 3. So I'm like, wait a minute. So let's flip-flop those points. 0, negative 7, 0. Negative, instead of negative 7, 0, 0, negative 7. Negative 3, 2, flip-flop. 2, negative 3. There's my 2, negative 3. 2, 3, flip-flop. There's my 3, 2 right there, right? So it's actually only this right-hand side. It's not that part of it. So it's only when x is greater than or equal to 0. So another way you can figure that out is which part of that quadratic is it. The domains and the ranges flip-flop. So the The domain on this is anywhere where x plus 7 greater than or equals 0. In other words, wherever x is greater than or equal to negative 7. That's the range of f inverse. The range would be y greater than or equal to negative 7. Well, you can see it. It goes y greater than or equal to negative 7. Now let's do the range on f of x. Well, f of x has a low of 0 and it goes up, right? So the range is y being greater than or equal to 0. That means the domain on the inverse, instead of y being greater than or equal to 0, will be x being greater than or equal to 0. So this has a restricted x values. It can only be the right-hand side of x squared minus 7. X being greater than or equal to 0. It comes from the range on the original. Okay? And there's, you can see a nicer little picture of those two, reflective about the line y equals x. All right, this one we don't need to verify, but let's go ahead and practice a couple more in finding our inverses. If y equals 2x minus 3 over x plus 4, I want to switch x's and y's. And now what I want to do is I got to get my y on top. So I'm going to multiply both sides by y plus 4. So again, I got to get my y on top. So I multiply both sides by y plus 4. And now what I'm going to do is I'm going to gather. Notice I have a couple different y's. I have xy. So I have a y over there. And I have a y over here, 2y minus 3. Get all your y's on one side. And get everything else on the other side. So I have xy minus 2y equals negative 4x minus 3. So what I do is I can factor out a y. So now I can just divide both sides by x minus 2. See how I can do that? So if I can factor it out, I have my inverse. Here's my inverse of f. Again, we don't need to verify that. Similarly on this last one, let's do this last one like that. So we got y equals 3x minus 5 over 2x minus 3. Switch your x's and y's. And now we'll go ahead and multiply both sides by 2y minus 3. So I have 2xy minus 3x equals 3y minus 5. Get all the y's on one side. Get rid of that 3x. Take that 3x over to the other side. So we have 2xy minus 3y equals 3x minus 5. And now we can factor a y out of both of those. And then we'll get rid of that 2x minus 3. So y is 3x minus 5 over 2x minus 3. In other words, that's our inverse. Notice if we graph the original rational function as well as the inverse, which is the rational function, you'll see that those things are reflective about the line y equals x. Well, thank you so much for watching. I hope that helps you get started on this. See you next time.